Cycle the recording. Hello everyone and welcome to Handmade Hero, the show where we code a complete game live on stream, except we've been on RSI break for 2 weeks, which we are cautiously going to stop being on RSI break this coming week and see how it goes. No promises. I don't know if it will go well or if it will go poorly. We will see what happens, but next week we will start back again, cautiously doing some coding. I don't think we'll jump into Handmade Hero coding. What I'd like to do instead is maybe do a little bit of for-coder coding, get ourselves a modal editor, which hopefully helps with the RSI as well. And assuming that that goes well, then the week after we can start back on Handmade Hero again, which I would like to do, and I'm sure you would like to do as well. In the meantime, as we have been doing, I've been taking questions that people want answers to, and I have 3 things that have come up that need addressing. 2 of them are quick, 1 of them is not so quick, so I will do the 2 relatively quick ones first. And the first one is from Twitter, which is a discussion that was going on at the moment involving Mr. Sean Barrett, the person who wrote the SDB libraries, which we have talked about many times on stream as being a good example of code that people can actually use that helps them. But this is the references prevent null pointers question. So I want to make it clear because I believe this is kind of a statement of fact and not a statement of opinion. So I want to make it very clear what the sort of concept is behind these statements and why this statement in particular I think is just objectively incorrect. Not subjectively, not a matter of programming practice, not a question of opinion, but actually factually wrong. And I want to be very specific. It's this word right here that is wrong. So I will now try to demonstrate to you why I believe this is just factually wrong. This doesn't mean you shouldn't use references. It doesn't mean that I would argue with someone who said that they prefer using references for various semantic reasons. It would not mean that I would say that someone was wrong who said they like to use references as a way of notating to themselves what something meant. All of those things may be fine programming practices that people can choose to use or not use based on their own personal preference. But this comment is just always incorrect, just factually as far as I'm concerned, and I wanted to explain why. Okay, so the reason is that if you are claiming that using references in C++ somehow prevents you from having null pointer, and when I say prevents you having null pointers, what we really mean is null pointer dereferences, right? And we all know what that is, right? That's if you have something like this, int star a equals 0, and then I do star a equals anything. This is attempting to write to a memory location. The memory location is 0, or as we might call it, null, right? Which just means it's pointing to nothing, and specifically so. This will immediately cause a fault. And we know this, we see this all the time. We've seen this on Handmade Hero when we've had bugs or something like this. We know that if we dereference a null pointer, we're going to get a fault. It's just like a divide by 0 or other things like this, where the processor can be programmed and put into various states that causes it to immediately trigger a hardware-style exception, not C++ style exception, but actually a literal, hardware exception in the case where this occurs. And the operating system will catch that and let us know. So this is a hard fault if this occurs. So obviously we never want it to happen in the run of our program unless something very specific and weird is going on and we have some kind of exception handling at the hardware exception handling set up to deal with it. We don't ever want this to happen. So it makes sense that a developer would always want to do things that would prevent them from getting into situations where they dereference a null pointer. It is almost always 99.999% of the time going to be a bug. Okay. So some people claim that using references instead of pointers prevents this from happening. And what does that mean exactly? Well, what they're saying is that if, for example, I was to make a function, in fact, I guess I'll make it void because it doesn't matter at this particular point. Let's say I had a function void foo, and I take an int star a here. And on the other side, I have a void foo that takes an int reference a, okay? And in this case, we have, this star a, and I'm going to say star a, equals 5. And in this side, I'm going to say a equals 5. These are essentially completely equivalent pieces of code as far as the compiler is concerned, okay? They will produce exactly the same operations. The only difference between these two pieces of code is that in one case I've used a reference, which means that semantically speaking, wherever I refer to a, I am talking about the thing that the pointer points to, because this really is just still a pointer, okay? Under the hood, it's going to pass a pointer. But in this case, I'm leaving the pointer as an explicit thing, so when I want to actually write to the pointer, I put a star in here, okay? Very simple, very straightforward. The compiler will, in both cases, produce some code that moves 5 to an address that is passed by the caller. But in one case, that address is passed as a reference. In one case, that address is being passed as a pointer semantically. That's it. So again, code is the same. Semantics are different. So now someone tells you, hey, if you write code like this, that prevents null pointer dereference. But if you write code like this, somehow it doesn't. The implication is this will catch some bug for you that this one will not. And my assertion is, show me how that's possible. Tell me what you're seeing that makes you believe that that's true. Because I am going to make a claim that will, I'm sure, ignite the people who make this claim. They will explode in a giant fireball of rage. But I am actually going to claim that, if anything, the opposite is true. Meaning this is the code that will create less null pointer dereferences. And this will create more. Don't believe me? Well, let's see if you believe me after we're done. Okay, so I've got two functions here I can call, foo star a, foo reference a. So what does that look like at the call site? Well, at the call site, it looks like this. I've got int b equals 6, and then I call foo address of b, right? On the other hand, I have int b equals 6, foo b, okay? Both of these will pass the pointer. Both of these will modify b so that it now actually says 5 instead of 6 after we come out of here. So they'll both do exactly the same thing, but on this side, I take the address of the b first, and on this side, I do not. Now, in this code, obviously, there is no way that we could have a null pointer dereference in either case, right? Because if we didn't have a pointer to begin with, then taking the address of it certainly isn't going to introduce a null. So no savings here. So let's take the only other case that actually exists, the one where we already had a pointer. So now we have int star b equals something, and over here we have int star b equals something. Well, in this case, I call foo with the b, and if perchance this was 0, this code will crash, right? On the other hand, if instead I called this with star b, which is the only way I can call it because I have to turn it into a reference first, guess what? This code will crash. No compiler warning, no error checking, no nothing. They're exactly the same. So tell me, where exactly is the compiler doing something to help me prevent a null pointer dereference? The answer is nowhere, because either you didn't start with a pointer to begin with, in which case neither code path crashes, or you did have a pointer somewhere to begin with and you needed to turn it into a reference, which means that code path will crash as well. If in either case you were trying to handle the fact that this could have been 0, you had to put in an if. And neither one will be stranger here, right? They're both exactly the same. That's it. So either the programmer is guarding against null or they're not, and it's whichever they chose to be, right? So again, in this particular case, if you were to tell me, oh, Casey, well, the way that I explain to somebody that something has to not be null in my functions is whenever something's passed by reference, they know that it can't be null. So that's a clue to them that they should check for if, right? Again, you want to make that statement and that's your code convention? Great. Like I said, would not argue with you. But the concept that the references themselves have anything to do with preventing a null dereference is wrong. And now I'm going to tell you why I think actually the opposite is true in practice. Why? Because very few programmers are actually any more diligent about not doing this than they are about not doing it here. They really aren't, right? If someone needs to call something and they don't think the thing could be null, they typically just do that, even if it turns out it really could have been null in some way or whatever happens, right? So, if you wrote this code, right? We'll go back up here for a second. If you write your code like this typically, then you're very likely to down here perhaps add some checking, right? But you're never going to add any checking here, and this gets a lot worse as you go down the chain. This might not just be one little function, but once I've turned it into a ref A, nobody I ever call is ever going to check that pointer again. Right? I could pass this through 17 layers of code all the way down to somebody at the end who finally uses it. No one's going to check it because it's a reference. It can't be null, right? So you get absolutely no fault tolerance. This is the no fault tolerance path. It means that you had better have been right everywhere, because if you were ever wrong, you will absolutely crash. Whereas this one, hey, computers are pretty fast nowadays. And if that's almost never false, is really not very expensive. You can throw a bunch of those in here and all of a sudden you've got some fault tolerance, right? This code is actually the code that's much less likely to have a null dereference than the other one. So the more you actually insist on using the references, the less likely you are to put any heat shielding on the code at all. Now maybe you should argue you don't need any heat shielding. Well, okay, great. Start showing me some of these C++ programs that don't crash all the time, because parentheses, all the ones that I use every day sure do, and then maybe I'll start to believe you. But the point is, from the actual implementation and semantic layer, if you want to talk about which one is more likely to produce code that has a null pointer dereference, I actually say it's this one. And the only way that this kind of code is ever better is if you magically have a team of programmers who never, ever, ever, ever forget to absolutely check every time before they change something into reference, which I rarely see people do. All right, so that's the end of that rant, and hopefully that makes it very clear what my position on that is, and I suspect that that is pretty close to what Sean's position on it is, but I don't really know. All I know is that he was of a similar opinion to me in the Twitter comments on this, where he was saying that he did not believe it to be a viable technique for catching errors. All right. Now on to the more meaty subjects. Because also, as a coder to this, I don't care at all about this, at all, right? This is one of those programming debate things where you're just like, who cares? If this is where you're at, that you think that arguing about this one way or the other for some extended period of time is like a good idea, like you're already fired. Like you're off the team. Don't even talk to me. Don't even look in the direction of our office because you're just going to make our code worse. All right, so let's move on to more profitable things. Knuckles, who is, I think, asleep at the moment. He is, I think, in Moscow, I want to say. He asked a question that I'm not sure I understood. So I'm going to try to answer the question, but I may just be answering a question that he didn't really care about. So I apologize, Canuckles, but here is his question. He wanted to know what the difference was between interpretation and translation. And as far as I'm concerned, it's a nomenclature thing. It's not the kind of thing I excel at. Pedantic specifically what does this term mean versus that term, not something I've ever been particularly good at. But I can give you what my reaction to that comment is, and hopefully it helps a little bit, or at least helps you look in the right place. So when I hear interpretation and translation used together, then again, like I said, I may not be understanding the question correctly, but what I'm thinking of is what happens with a binary command stream. So machine code, right? Let's say, as an example. So x64 instructions, like an executable, something that the processor is executing, all right? If I say I am going to write an interpreter, and I spell it right, if I say I'm going to write an interpreter for x64, then what I mean is I'm going to write a piece of code which itself is actually running, and it's going to look at the individual pieces of the instructions as they would be executed, and it's essentially going to act like an Intel CPU. So it is software that is acting like an Intel CPU, stepping through, pulling out pieces of the code, and actually running them using its own simulated model for what should happen. Okay? So it's basically like a software version of a CPU. So it's running on a CPU, but in itself is sort of a CPU that's doing sort of the work of, okay, read the next byte. What does that byte mean? Okay, read another byte. Okay, that's an instruction. What do I need to do with that instruction? I need to add. Okay, where's my code for add? Jump to the code for adding. Where's my registers? Oh, they're here in memory. Pull out these two things that are, registers, add them together, put it back in another register, right? So it's actually a complete piece of code that basically emulates what a CPU is doing in hardware. It's actually doing that in software. So an interpreter is more or less an emulator. Those are not particularly different terms to me. Yeah. Translation, on the other hand, implies a single process applied once that produces a new piece of code. So again, this is interpretation. Translation is when, let's say I have x64 code and I need ARM code. Okay? Well, if I wanted to run some x64 code on ARM, I could use an interpreter. I could write a piece of code which runs on ARM, which reads an x64 instruction stream and has a simulation of an x64 CPU in it, and off it goes, right? It just does the operation, does each operation as it goes. So it's basically code for an x64 running on top of an ARM, right? So the x64 part is in software, the ARM is the hardware, and it's running an x64 emulator essentially on top of ARM. But another way I could do it is with a translator. And what that does is it takes an executable written in x64, right? So it's x64 native, and it actually just translates it into an executable meant for ARM. So it does the same sort of process of reading the x64 instruction stream, but instead of trying to execute it as it reads it, it just tries to translate it over to a different instruction set, perhaps one that's native to the processor that I'm on now, but perhaps not. I could be doing it to a PowerPC, for example. So I could have a ARM CPU running a translator written on it that translates x64 to PowerPC if I wanted to, right? And then once I've translated it, I've got a PowerPC executable. I can go run that on a PowerPC native, or if I had an interpreter for PowerPC code, I could run the PowerPC code through the interpreter and see what it did, right? So that's, assuming that I understood your question correctly, I'm not sure if I did. That's interpretation versus translation in my mind. And so I hope that helps if that was actually the question. If it's not the question, please feel free to email me sometime. and just tell me what the actual question was, if that makes sense. All right. And so now we get to the question that I think will probably take the majority of the time on this stream, which is sort of, I'm going to broaden the topic a little bit even from what the question was that was asked, and it was asked by Elvin, who I don't know if he's here today. Oh, I think, yeah, I saw him. I think I saw his name go by. It was asked by him in email, and what he was asking about was the sort of time-honored process, especially in older times, although still happens to this day, the time-honored tradition of games using offline rendered art for certain elements while still using real-time rendered art for other elements. And now this can be as, you can think of it, the very earliest version of this is just the fact that we have like sprites, right? The fact that we pre-rendered some images somehow, maybe they were hand-drawn, whatever, and then we're compositing their locations and changing their locations. That, in a sense, is using pre-rendered stuff and composing it at runtime, right? But those techniques continued to get more and more elaborate as games went on, until some of the ones that Elvin was mentioning in his email, for example, Final Fantasy VII, where you had a 3D rendered character who was running around on 2D pre-rendered backdrops for the overworld maps, for example. Or games like Resident Evil, which had pre-rendered backdrops and 3D characters and monsters and stuff like this moving around on top of them. And as he pointed out, some of those games actually had very elaborate effects they might do. So, for example, they might have a situation where a character is standing on the floor of a pre-rendered backdrop, and you're seeing the character who is being rendered in 3D, but you're also seeing their reflection in the floor, even though the floor was a pre-rendered thing, right? And so hopefully you've all seen some games that do this, or maybe even non-games that do something like this. And what Elvin was asking is could I sort of give a general overview of this and how you go about doing that, what the sort of techniques are, how they work, that sort of thing. And so I kind of wanted to broaden that topic a little bit and just talk about it from the standpoint of the sort of category of algorithms that this falls into, which is actually broader than just this specific application. It's a category of algorithms, and I shouldn't say algorithm, it's a category of computing, a category of something. I don't know what you want to call it, but it's a well-defined term. It's called partial specialization. And you could also equivalently call it partial evaluation. And what this means is actually very, very easy to see if I just write a very simple piece of code for you, and it generalizes all the way out to Resident Evil, right? It's kind of interesting. So let me show you what this means. So normally what happens in a piece of code is you have something that maybe looks like this. Let's say I've got a function, my ubiquitous foo, or actually, you know what, I'm going to return an integer foo, and it takes an int a and an int b. Okay? And I'm going to write a function here. So I'm going to take it and produce my int c, which by the way will be my return value. I'm going to take an int c, and the way that I'm going to take to produce my int c is I am going to take 5 times a, and I'm going to add it to 6 times b. Okay? So this is a function that hopefully everyone understands. It is extraordinarily simple. It does some of the most basic things you could possibly hope to have done in a function. And you can see that it is, in fact, a functional thing, right? This is when we talk about functional programming, right? It's something which has no side effects. It simply produces a result, and that result is based entirely on its 2 input parameters. And it is entirely dependent on those 2 input parameters. Change a, and you will get a different return value. Change b, you get a different return value. It is fully dependent on both of them. Now let's suppose that I am in a situation where I don't know, we're on the world's most primitive CPU, we're all the way back to the old days, and this is actually something that's expensive for us to compute for some reason. Now, nowadays, that's a laughable concept to even say, but let's suppose we were, because as you can imagine, when we generalize this out, that is the sort of thing we're going to be thinking about. But in our specific case, let's pretend for some reason that we profiled this program, and somehow this took tons of time. Like this took 80% of our time, this line right here. And we look at this code and we go, what can we do? How can we optimize this program? Because we need to do 5 times A plus 6 times B. All of our time in the execution of this program is spent there, and we simply just don't have the computing power to actually do it. What do? Well, we analyze our code and we find that, say, in 50% of the cases, and maybe I'll change that to a little bit more of a breakdown. In 20% of the cases, B is 7. In 30% of the cases, B is 9. In 25% of the cases, B is 10. And then the rest, B is random. Right? So let's suppose that I did this analysis. Well, now, when I'm looking at this, I'm going, okay, well, 20%, 30%, that's 50%, plus 25%, that's 75% of the time. I actually don't really need to do this operation, right? I mean, I kind of already know what it is. So wouldn't it be a good idea to create 4 versions of foo, each one being specialized to a certain parameter space, while still allowing some freedom in the rest of the parameter space, right? And maybe for good measure, let's say that we actually knew it entirely, just to make it a really great case for us. Let's say we always knew it was 7, 9, 10, or 15. Now we know we could replace foo entirely with just foo 7, foo 9, foo 10, and what I say, foo 15. We could create 4 functions, and each of those functions can be specialized to actually have a hard-coded constant in here for b. So now, instead of computing this, which is 2 multiplies and an add, I go down to having it be int c equals 5 times a plus some constant, right? So now we remove one entire multiply, which is a third or more of the work. And let's pretend this processor multipliers are very expensive. It could be more than a third of the work, right? And we just have a different one, different constant for each of these things, right? Similarly, what we could do instead is just have the same foo, but instead of 6 times b, we just have it so that we pre-know which one it is, right? And we pass in 6 times the value and get rid of the multiply. So that's partial specialization in a nutshell, right? It is specialization because you are taking a general equation and you're specializing it by removing some of its parameter space. And it's called partial because we are not specifying all the parameters, we're only specifying some of them, right? So we're knocking out this part of the parameterization, but we're leaving this part in. And that's where the partial comes from. So how does this apply to Resident Evil or Final Fantasy or any of these games? Well, if you think of the 3D rendering pipeline as basically a giant equation, right? Something where I'm going to render a bunch of things and then I am going to display them, and there's multiple steps involved in this and there's a lot of work that has to be done. You can think of any given pixel as essentially having that equation, right? You can think of it as having an equation there. And for example, if I was to render something like, let's say I do a full 3D render, again, no tricks here, no 2D, no nothing like that. Let's say I'm going to render something, I have a screen, and I'm going to render all my stuff. So I've got a bunch of complex geometry back here, you know, maybe it's like some kind of a hallway thing, and maybe there's like a bunch of wood slats and a door thing, and you know, there's all kinds of like, you know, stuff on the walls and a torch and who knows what, and I don't know, that sort of thing. And then there's just like an ogre here. And maybe for good measure, up in the front here, there's like a little altar thing, some kind of sacrificial altar, you know, that's in front of the ogre. Well, if I was to take a look at one specific pixel here, let's say that I'm going to take a look at a pixel that's right there, okay? That's that place right there. Well, if I'm to look at that, well, what do I see? The equation for that pixel, right? And equation kind of a loose term here. The program, right? The code. The equivalent of int foo for that pixel, if I rendered everything using the Z buffer, doing whatever the game was doing, might look something like, all right, first I have to do, you know, the door pixel here. So that's like whatever the door material is, right? Door material, and then I have to like light that using the complicated light equation. So I'm going to start off with my base color for this thing, right? Base color is going to be like called the lighting equation on the door material, using, you know, 50 different lights, some light array, who knows, and it's going to do, this is super expensive, does a bunch of ray casting, who knows. Then I'm going to have this ogre, right? I've got my ogre here. That's not how you spell ogre, right? So now I've got to do my ogre, because it turns out the ogre overwrites this. So you know what? I'll just call this the output color. So the ogre overwrites this. It says, okay, you know, whatever this guy is here, this output, you know what? I'm going to do this even better than that, I think. I'm going to do this even a little bit better. I'm going to say that we do out equals light there, and then I'm going to say if, you know, the ogre's z value, right, is closer than the door's z value, okay, then we're going to come in here and say, all right, well, then the out color is whatever the ogre is. So I've got the ogre, and I'm going to have to light that guy, right? It's got the ogre here, and the ogre is like a dynamic guy, so maybe he's not lighting as good, so maybe there's a single light that gets passed in here, I don't know, right? And then finally, if the altar's z is closer than I guess the out z, this should really be out z here, there we go. Then the current out z, then I'm going to say, okay, well, now we've got to light the altar, so there's the altar's thing, and then there's that light array again, and so on. So yeah, again, is this really happening exactly like this? Not exactly like this, but you can think of it as being very much a function that produces the color of the pixel, right? The GPU is essentially, or I should say, let's say this is, again, ignoring GPU, ignoring all that stuff. We're just writing some kind of offline, crazy expensive renderer. It's Pixar, it's who knows what. We're creating the full version of this thing that's beautifully lit and all that stuff. Then you can imagine it looking a lot like this. It's like, all right, well, we start off by saying, we've got something here. We've got the door. We're going to evaluate that first. We're going to do all our lighting calculations and all our material calculations. We're going to produce an out value. The out has a color and a z value, which is how far it is from the camera. We're then going to say, okay, now we got that ogre's there. If the ogre's point at this location on the screen is closer than the one we just computed for the door, then we're going to overwrite him, right? And here we go. We compute the ogre values, and when we overwrite the color value with that, finally, if the altar was closer than the ogre at that point, then we're going to go ahead and do the lighting and so on. And now we know that since we're talking about a pixel here, we know that actually all we end up caring about is this value, because the altar was actually there, and it was in front of these guys, right? And you could also imagine the torch being in here as well. We don't happen to hit the torch, but you could imagine it being tested to see if it was, all that sort of stuff. Okay, so essentially what happens when you're talking about a thing where you did like the Resident Evil model or any of that stuff, is we're still just talking about partial specialization. What we're talking about is saying, okay, there's this giant, really complicated function that's happening to compose this scene. But if we were to say that, for example, this term and this term, we're going to be partially specialized, right? We're going to partially specialize to those. Then all we would have to compute at runtime is this one, right? If we knew what the door color was at that pixel all the time, and we knew what the alter color was at the pixel all the time, and furthermore, we knew that since you can only see one or the other, right, we know that we can just store the alter's color as the only one at that point in pixel. Well, we can produce an image that is essentially the partially specialized constants necessary to reconstruct this function if we have the ogre, if we still do the ogre at runtime. And how would we do that? Well, like I said, we know that this guy can never be visible. So the first thing we can do is just say, well, if we take out the ogre, and we're just talking about partially specializing these two, we just need whichever one's closer. So when we actually render everything minus the ogre, we'll just keep whichever one's closer. And we know that this one's closer, right? We know that's true. So we don't need this one anymore. But now what do we need to keep? Well, we need to keep two things, right? First of all, we need to keep whatever that output color was. Because if there's no ogre there, then we know that this is actually going to be the color of the pixel. But we need to keep something else as well, right? We need to keep the z value because we needed to test the alter z value against the ogre z value in order to know whether we're supposed to draw the ogre or the alter. Because the ogre could move around in front, right? And then it would be the ogre that shows up. And that, just by, again, thinking through what the function, what the actual graphics function is that you need to evaluate at every pixel is, it directly tells you exactly what you would need to store to reproduce what you wanted to do after you partially specialize. Color and z value. And that's exactly what you store if you want to do post-compositing. You store the color map and the depth map. And then at runtime, when you do your real-time rendering, you just real-time render into a context where you already have the depth map, so it'll test against the depth map, and if the depth map is closer at that pixel than whatever the thing is that you're rendering, then you don't put anything there, and you let the color map that you saved show through, and if you do find that it is closer, then you render the thing, right? And so partial specialization as a framework for thinking about these things lets you understand immediately what you might have to pre-render and save in order to reproduce any kind of complicated thing you might want to reproduce, any kind of complicated scenario, given some things you're willing to specialize around. And so in this case, what did we specialize around? Well, you could think of this as taking the location of the door, right, and the location of the altar. Originally, those were movable, right? You could also say the location of the camera. All of those things, right, were originally parameters, and I guess obviously the ogre as well. So we had a function that was taking the door, the altar, the camera, and the ogre, and it was able to produce any image we might want to produce with any location of the door, any location of the ogre, any location of the altar, and any placement of the camera. And then what we wanted to do, again, Resident Evil style, if we're talking about a fixed camera location with a fixed scene and only like one or two moving things, is we just said, we'll partially specialize everything except for the ogre. So the camera's fixed, the altar's fixed, the door is fixed. Now all of this stuff mushes down, and we're left with just a color map and a Z map for our sort of image that we start with. And all we have to do is render the ogre and depth test him against the depth map to know whether we pick the colors from our pre-rendered result or the colors from our real-time rendered result. Okay? So hopefully that makes some sense, but you're probably wondering, why did I go through all this trouble of explaining partial specialization if all I'm going to talk about is color map and depth map? And the reason is because I want you to start thinking about it a little bit more broadly. Don't just think color map, depth map. Think anything I want to compute, right? So let's take another case, like in Resident Evil, where I have a scene that has a floor, okay, and there's stuff, behind it or whatever, and here is my guy who's standing on it. I now want to render reflections of the person in the floor, okay? So now you're in exactly the same situation that you were before if you understand partial specialization. as long as you can write the renderer for this offline, as long as you can write the code that would have rendered it, you're in an excellent position to figure out what you need to save to do it runtime with the background fixed. So, what might we need? Well, it depends on what our goals are. If only the floor is reflected, right? So it's just the floor, which in Resident Evil it was. Then we get a little bit of a bonus, because the floor is just a plane, and a plane has an equation. I don't know if we ever covered this on Handmade Hero, probably not, but the equation for a plane is ax plus by plus cz plus d equals 0. I'm sure we'll get to this some point, probably not. I guess we did equations for walls, which was basically the same thing. And so A, B, C, these things, the ABC actually is the normal to the plane, right? So if you imagine there's a plane and there's a vector pointing out of it, the ABC is actually this vector right here. That's the normal. And the D value is how far from the origin you would have to go backwards along that value to get to a point on the plane. Neither here nor there. Doesn't matter at all for this case. Just thought I'd mention it. But point being, we need a plane, right? We would need the reflection plane, because we're probably going to need that to set up the reflection in the runtime version as well. But point being, so what are we going to need here? Okay, so we've got our foo, and we're going to need sort of whatever the scenery is that we're going to render. I don't know what this guy is. I played like one Resident Evil game. I think it was Resident Evil 0. Let's say, is there someone named Veronica? Maybe? Or something. Let's say this is Veronica. I don't actually know, but maybe that's Veronica. I think you can tell just clearly from this drawing. It looks like a Veronica, doesn't it? I mean, it says Veronica to me, clearly. I feel like she also had like a beret on or something. I don't know. Maybe not. Point being, let's suppose that that's Veronica. And let's suppose that Resident Evil is a story about someone named Veronica, which it probably isn't. And what we need to do is we need to pass in Veronica, right? Then we also need to pass in the plane of the reflection, right? That's what we got to pass in. All right, so now we have our code, and we need to actually write the code for this. Well, it's basically exactly the same as the code we were going to write before, for the most part, right? Again, just pseudocoding it. I got to produce an out value, and so what I'm going to do is I'm going to light, my scenery with some lights. And I suppose I should have listed the lights before here too. I mean, right, there's so much stuff that's being partially specialized out in one of these things. The light array is all in there, right? So we have a light array, and then we also have a primary light, and we chose to specialize out all the other lights, but just keep one of them for lighting our ogre. Again, if you really want to write it all the way out, if I was being very diligent here, you could see that we're specifically choosing the light and the ogre as the still varying parameters, and everything else gets partially specialized away, right? But in some sense, that's really not sort of true. This is even getting partially specialized away. Really, what's happening is we're using an approximation for this, but neither here nor there. Again, not super important. So here we are. We got to light this thing. So we light the scenery with our lights, and we produce whatever that is, and then we need to do our out here. We need to light our Veronica with our lights as well. And then we would have our proper scene with no reflection, right? But, like I said, we do want our reflection there. So what we need to do in between these two, you might say, like, in fact, let me go ahead and put that in here, right? Is we need to do our standard if. We need to say, like, if Veronica Z is less than the scenery Z, then the out equals light Veronica lights. But what we need to do here is we need to say, well, okay, we were sort of saying that we wanted this reflection to occur. And so far we have not had any way for the reflection to occur. So what we need to do there is we need to have some parameter that tells us how reflective the scenery is at any given point, right? So when we compute this and when we render it, this would be a property of the materials in the scenery, how reflective it is. And if that thing is marked reflective, then we need to create the reflection for it, right? So what we need to do here is we need to say if whatever our out.reflection is, if the out.reflection is greater than 0, then that means the surface at this point is reflective. So we're going to have to compute the reflected Veronica, right? And really the reflected everything, and we're going to have to render it in there, right? Now, fortunately, we already have what we need. If we consider our foo to take a camera position, then right in here what we would do is say, all right, when we have our reflection, we are then going to go ahead and mix our output color, right? And using that output reflection value, let's say, we're going to go ahead and mix that with just another call to ourselves with the same scenery, the same Veronica, and now the camera is going to actually be reflected, right? So you can think about this as basically saying, all right, we're going to have to create a reflected version of the scene, so we're going to create temporarily a fake camera, which is just pointing in the direction we would need it to point in order to render the scene reflected, and that would involve a mirror and all that stuff. All that good stuff that's outside the scope of what we're talking about here, because again, I'm trying to sort of avoid the talk about how you actually render these things, because that's a how do you do offline 3D rendering talk, which is a whole other thing. But assuming that you do know how to create the actual reflected version, you're going to want to do that and then mix it into the color at this point, right? So now you can immediately see what actually needs to happen in order for you to get the correct color at this point. Now, instead of just the Z and the color, right? We need the color and we need the Z because we need to save those. We can partially specialize this part right here, but we still have the possibility that Veronica is going to be reflected. So what that means is we need another map, right? We need a map that tells us whether something is reflective at that point. So we need to save all three of these, plus we need to save the plane, because remember, we need to be able to create that reflected camera at runtime too for rendering the reflected Veronica. Because the fully partially specialized version of this thing includes the recursive call to itself that has to render Veronica twice, right? It has to render Veronica once normally and once in the reflected camera. So now you can see that we actually need to store three maps, potentially. One that's the color, one that's the depth, and one that's the reflectivity at that point. And by the way, this gives you, because there's another parameter here, again, that gives you pretty much, I guess what I should say is, this equation, this sort of stuff that happens with the blending here, can be as complicated as you want. It just may mean that you have to start storing more things. This is just standard material rendering equations that you would be doing here in your offline renderer. Any one of those things that you need to, that depends on, when you look at the actual function, that depends on a dynamic element that could move around, you have to, anything that you can't condense down into folded constants, right? Anything that doesn't collapse out as constant, that still depends on a varying parameter, those things have to be stored as maps, because they have to be read again, right? In much the same way that you can't get rid of Z, because you need to test it against something that is not known at partial specialization time, you need to store reflection because it needs to be tested against something that is not known, right? This thing that's going to be tested against it, this extra rendering step, has a dynamic element in it, ergo this if cannot be optimized out, it cannot be specialized away just by looking at what actually happened on that pixel in the offline render stage. So in a lot of ways, this is very similar to the concept of optimization, right? Partial specialization is very much like what an optimizer does when it takes your code and sees that there are constants that it can deduce that allow it to remove whole portions of that thing. And furthermore, it's exactly like what happens in, like when you have an inline function, let's say, and you call it in multiple places, it may produce multiple different versions of that inline function as it gets inlined that are based around the conditions that surrounded the call to the inline function, because it can see some things are constant and can be optimized away. In some cases, can't necessarily be optimized, or the same things might not be optimized away in other cases, right? And so that is the way to frame these kinds of problems, right? What you want to think about when you want to think about how do I offline do a bunch of work, you want to think about it in terms of partial specialization. Sit down and actually write the full rendering concept. What do you want to actually compute at this point? If you were writing a ray tracer, what would you actually, and had all the time in the world, what would you actually compute? And then you start condensing that work into pre-computed values. This is exactly, again, the same thing as light maps, right? Let's elevate it up to 3D rendering now. Forget Resident Evil. Think Quake, all right? Now we've got a situation where we've got these walls. They're being rendered in 3D, okay? And we're actually be able to move around them. So the camera is no longer fixed. It's no longer in a single location. It's not like Resident Evil. We can look anywhere. We can go anywhere we want. But it's still way too expensive to compute the lighting. The fundamental rendering equation at any pixel that we wanted to compute involved not just the diffuse color of the texture at that pixel, which we can reproduce at runtime now, but also a bunch of raycasts into the environment that look at where the light is coming from. So hey, guess what? We partially specialize again. Instead of calling light, this wall element with some kind of crazy array of lights, and the rest of the scenery and shadows and all that other stuff and material parameters, you know what? We're just going to consider that a constant that we compute offline, and we bake it into a map that we look up that now, instead of being mapped to the screen, is mapped to the wall. And even to this day, a huge amount of what happens on a 3D engine rendering team in terms of what they're actually doing, it's partial specialization. What they're sitting around doing is trying to figure out new ways of capturing stuff that they can render and compute offline while still maintaining the maximum amount of dynamic activity at runtime. And as 3D graphics has progressed and as processing power has gotten more and more and more and more abundant on gaming machines and gaming hardware, they're able to move things from what was previously partially specialized into things that are now dynamic. And the story of 3D graphics and progress as you move from, Resident Evil to Quake to something like Call of Duty now, or, whatever, pick your current Frostbite engine, whatever you want, Unreal. The story of that progress is constantly changing what we partially evaluate and why, right? And moving more things to dynamic and changing, getting more richer equations that we're trying to simulate as we can do that, and partially specializing different parts of them. That's really what's going on. Because at the end of the day, we know what we're trying to do. We're trying to evaluate the rendering equation, right? Jim Kajia's rendering equation, right? We're trying to evaluate that for every pixel on the screen. And we've never had enough horsepower to do it. And so everything we do is an exercise in partially specializing that equation. And there's so many ways to do it. And it all just depends on what you are holding fixed, right? Resident Evil was, let's fix the camera, let's fix the environment, let's fix the lighting, and we'll just render the dynamic characters, right? Quake is, let's just fix the lighting, right? We'll let the camera vary, we'll let, blah, 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 but we'll just fix the lighting and the shadows. That's not dynamic, right? And even in something like Quake, you can see they actually partially specialized part of the lighting equation and not others of it, right? Direct lighting was actually still computed in the Quake engine, and often is in most engines today, right? But the indirect lighting has to be pre-computed because it's too expensive to compute dynamically a lot of times. And so you often either pre-compute it, or like some engines nowadays do iterative refinement to sort of constantly pre-compute the lighting, if you will, so that you can have some measure of dynamic lighting happening, dynamic indirect lighting happening as geometry potentially changes in the game. So like I said, I kind of wanted to broaden that topic because really the concept of what Resident Evil was doing or what Quake was doing, they're all kind of the same concept. The concept is you have an equation you'd like to do, it's incredibly expensive, there's no way you're going to do it at runtime. What do you partially specialize? Which terms of it do you start folding out? What do you pre-compute and what do you keep? And you can do a remarkable amount of stuff by choosing to keep certain things as maps, right? That are either screen space or mapped onto geometry or whatever. You can do a remarkable number of things there. You can do a lot of interesting and different effects just by saving different elements of the process. So that's about it. And I think we're sort of roughly out of time. Hopefully that made some sense. And I don't know if Elvin is actually here today. He was the one who originally asked the question. But hopefully that answered it to a significant, to enough precision that he's sort of he sort of gets my my mindset on it anyway. Let's look at the chat. What is going on in the chat? How is the chat going, guys? We got time for a couple questions, probably. Oh, so Elvin is here. This, for me, is by far the best Handmade stream ever. Well, all right. I'm glad. I hope that means your question was answered. A couple of questions. So I guess they did something similar to Reflections to implement real-time shadows. Yes. How did they achieve other effects like camera panning and lightning? You still need an invisible level collision mesh, correct? So I guess what I would say is, again, there's... Let me take that two things. So let's say I want to implement lightning, right? Well, I can decide what my original lightning equation was. If my lightning equation is going to... let me give a very simple example here, right? So if I have a way to compute some lighting at a point, so this is an offline renderer, we're ray tracing our thing, whatever. I'm going to compute some lighting, and I'm going to say, okay, I want to light the scenery, and I'm going to give it this light array, and this is all the lights in the scene, and it's going to produce the output color, okay? You can also imagine me doing this. And I'm not going to call that out. I'm going to call that A. You can also imagine me lighting the scenery with just the lightning light. Right? Now I have two potential lightings for the same scene. And I can blend between them. And I wouldn't blend between them because lighting is additive. So really it's A plus TB. Is what it would actually equal. This is the out color, right? Where this is how much lightning. Now I've got lightning, I've got the scene lit just by the lightning, and I've got the scene lit by all the normal lights in the scene, right? And I add them together at runtime. I can dial this between 0 and 1 to turn the lightning on or off. Or even part of the way, if I want it to kind of fade out over a couple frames or whatever, right? I can do 1.7.20, 1.7.20 for that lightning look or whatever, right? Because fundamentally, light is additive, right? Lights add together. I shine a light on something, I shine another light, they add together the amount of light that I see. So it's completely separable, which again means it's great for partial specialization. So this means if I want to, I can just spend more memory to store the A and B separately. See, normally what I'm doing when, in a Resident Evil scene, I'm rendering it, I sum up the lighting for all the lights, right? That partial, but when I said light and I say scenery and I'm like light array, sorry for the scribbles here, I'm talking too fast, I gotta write fast. What does this actually look like if we actually start looking at the actual equation? Well, it's actually a series of like light the scenery with light A plus light the scenery with light B, and on and on and on, right? It's just a sum. Take the contribution from light A, add the contribution from light B, light C, light D, light E. If I had infinite memory and didn't care, I could store each of those as a separate map. And then at runtime, I pull from all the maps, I add them together, and I get my result. Now, why wouldn't you do that? Well, A, it takes way too much memory, way too much DVD space, and furthermore, your graphics card may not be able to pull from 30 textures at the same time. That may be too much texture bandwidth for it, right? I mean, 30 full screen textures nowadays on like a, crazy NVIDIA card actually isn't too much, but on a PlayStation or whatever they had for Resident Evil, it would have been, right? But point being, this is an entirely separable equation, which means that each term of the equation could be stored as a separate color map and added back together at runtime, which means that if you wanted to, you could actually control each individual light at runtime. And in fact, you can actually see this being done in a different domain just by looking at, for example, something like Maxwell Render, where they use what's called multilight. And what multilight is when they actually compute the fully Metropolis light transport solution, like the Monte Carlo integrated ray trace version of a scene, they just store whichever light's contribution they had computed, they store that to a separate map, which means that it's free for you after the fact to just dial the lights up and down and back. So this is actually a single image output from Maxwell Render that someone is now playing with the light sliders from. Same exact thing can be done in games, and I don't know the light that I've never looked at. In fact, I don't know anything about Resident Evil's lightning or how they did it or whatever. But point being, the general solution to that problem is actually very straightforward. And in today's universe, where you actually have a tremendous amount of memory typically to work with, it's not a big deal for you to pre-render 3, 4, 5, 6 lightings for a scene and grab from 2, 3, 4, maybe even more of those when you compose the scene at runtime. So if you were doing a Resident Evil today, you could have a lot of control over the lights, could be dynamically flickering and doing whatever you want, and they'd actually cast the correct shadows and all those other things, right? So that's certainly very easy to do. Now, the problem that you run into if you do this ain't with the background, because like I said, perfectly separable, really easy. The problem that, of course, you always run into is your dynamic objects. Those are still being rendered at runtime, and those are obviously more difficult to deal with because you've got to do dynamic lighting on them. Now, 4 lights on a character, not a big deal, but remember, the environment is not really going to respond properly. The fact that the guy is standing in front of the doorway isn't going to make the rest of the things behind the doorway darker because all that lighting was pre-computed. And so again, you're always limited when you do these partial evaluations. You're limited because now all the things you might have liked to have had dynamically computed are no longer being dynamically computed. That's just an artifact of freezing some of the things and approximating some of the things. So yeah. And it looks like also you had another question, which is you still need an invisible level collision mesh, correct? And the answer to that is, of course, yes. You don't necessarily need a collision mesh, but you need some way of knowing where the character can and can't walk, because you no longer have necessarily any level geometry because you're just storing an image of what it looked like you rendered it offline. So you need to store something that tells you where you can go, some kind of a walk map of some kind. And that could be level collision geometry, that could be a pre-computed set of polygons that you walk around. But you need something. As for how they implemented real-time shadows, I suspect they just used a planar projection of the person's geometry onto a plane. that again was pre-computed and sort of placed there, but I don't really know. Like I said, I've never really even played Resident Evil. What if you're constrained on space as well as computing power? Could you pre-compute parts of your graphics, e.g. a shape from multiple angles of 5 degrees, then do interpolation to get values that lie in between, e.g. a view of the shape at 7 degrees? Well, if you're constrained on space and computing power, then there's not much you can do, right? Pre-computing is the act of trading space for computing power, or rather using space to eliminate some of the need for computing power. So if you're constrained on both of them, it typically is not a win to pre-compute things, right? Because if you're constrained on both, you don't have extra space that you can use to store pre-computed results. All right, I think we're all good. So I'm going to wrap it up. I'm just going to add a little sort of coda here, or a little sort of note. So partial specialization, like I said, a really good way to think about this, and the idealized way to think about this. But what I'll also say is, obviously, there's always also this, right? Because sometimes when you're looking at this, in fact, often, you'll get to a point where you're like, well, there's no way to actually partially specialize this per se, but I could just approximate this term with something else entirely, right? So plenty of the things that you end up doing are partial specialization, yes, on a good day, but on other days, you're straight up replacing a term with something not as good, right? Because sometimes you partially specialize and you really are still computing the same thing, but you're just not allowing it to vary at runtime. And that's pretty good. You should feel good about yourself doing that. Yeah, you lost some dynamism, but you're still producing the same equation, and that's pretty cool. Other times, you can't even do that. And if you can't do that, hey, you know what? The story of 3D graphics, there's a lot of hacks. So what can you do? So don't think of it as always having to be perfect partial specialization. That's not true. A lot of times you do just have to straight up hack it, and that's fine too. But partial specialization is still a really good framework for thinking of it in, because even if you just allow kind of a hack in there, it's like, okay, this wasn't really partial specialization. This was just I straight up replaced the term with a simpler term. You know what? Still a good way to think about it, right? Is to start with the real equation and know what you're simplifying, know what you're partially specializing. Because that always tells you where your room for improvement is, and it also keeps you very close to a good result, and you know where you have cut corners, so there's no surprises, and that's kind of nice. That's it for today. I'm going to wrap it up. Thank you, everyone, for joining me for another episode of Handmade Hero. This is the end of our chat streams. We're going to try coding again next week. We'll see how it goes. No promises, but we'll make an attempt. Till then, if you would like to be kept up to date on the schedule, this is the place for it. Tweetbot right here. The Tweetbot tweets the schedule at you. You can see that luscious schedule right there. So there will be another one popping up here this weekend that tells you what the schedule is for next week. Check it out, subscribe to it, or follow it, or whatever you have to do on Twitter to get notifications if you want, to catch the stream live, and I hope you do, because it would be nice to see you back here next week for some 4Coder work. Until then, have a good weekend of programming, and I will see you guys next week. Take it easy, everyone.